right, let's look at an example problem from chapter 2. This is number 47, taken from the end of the chapter. And it says, at a construction site, a pipe wrench struck the ground with a speed of 24.0 meters per second. A, from what height was it inadvertently dropped? B, how long was it falling? C, sketch graphs of Y, V, and A versus T for the wrench. All right, so this is a solid problem. It's right near some problems that are assigned on the homework. So let's follow our full problem procedure. So think for a moment, what's our first step in approaching a new problem? That's right, it's to draw. Or if you didn't say that, now you know. First step is we want to draw a picture. And I'm going to leave it small for now so that we can keep looking at the problem statement, but I will, when we get to the calculation part, I will make it just the whiteboard so you can see it better. All right, so what am I going to try and draw here? Well, we have a pipe wrench, a construction site, and the pipe wrench is striking the ground. Okay, so that's something we want to have the ground, the pipe wrench. I don't actually know how to draw a pipe wrench, but that looks roughly like a pipe wrench. We can pretend it is, and we know it's striking the ground. So I'm going to draw it with a velocity that is going downward. Cool. Notice in this problem when it says it struck the ground with this speed, it's not focusing on the speed after it struck the ground and comes to a stop. It's just focusing on how fast is it going before it hits the ground. All right. What else can we draw? Well, notice in A it says from what height was it inadvertently dropped? Ah, that tells me I need to also draw a height for this pipe wrench to have come from. So who knows what the scenario is? I'll draw some sort of building with, say, a person. And the person has their mouth open because they inadvertently dropped it. Probably can't see that yet, but that's okay. You're saying, oh no. All right. So this is pretty good as far as getting started with a picture. So I think we can go on to our next step. What's our next step? The next step is going to be to write down everything that we know. This is often going to be the numbers that are given to us in the problem, but it can also be information that's inferred from the problem statement. So one number that jumps out at me is this 24.0 meters per second. And that is some sort of speed or velocity. So I'm going to say that that is V. And I'm going to use V without the not subscript, without the 0 subscript, because it is when it strikes the ground at the very end. So I'm just going to leave it as V is equal to that 24 meters per second. And then this works as a speed, right? It says it's a speed of 24 meters per second. If I want to write as a velocity, I'll need to include a positive or a negative sign to indicate direction. So at the end, when it strikes the ground, is it moving in the positive direction upward or the negative direction downward? Well, it is indeed going down. This is one place where our picture helps us. So I'm going to make that a negative 24 meters per second. Negative signs are really easy to miss, so you have to pay attention to them. All right, what else do we know? I'd encourage you to think about this for a moment, see what you can come up with. And so in the meantime, while you're thinking, go ahead and pause the video. All right, did you think about it? Well, there's a few other things that we can come up with. One is that in part A, it mentions it was inadvertently dropped. If you inadvertently drop something, how fast is it going when you release it? It's hardly going, right? It's just, for a brief instant, it's not even moving. It's not that the person flung it down or tossed it in the air. They just inadvertently let it slip from their fingers. So that tells me that the initial velocity at the top is equal to 0 meters per second. So that would be, say, up here, O is equal to 0. All right, so that's some inferred information. Another thing we can infer is the problem doesn't mention this is taking place on Mars or the moon. So if it doesn't specify, it's going to be taking place on Earth near the surface of Earth. That is a reasonable assumption. And the pipe wrench is falling through the air near the surface of Earth. What does that mean? That means it's in free fall. And if it's in free fall, we know the acceleration. The acceleration in free fall, A, is equal to negative g, or negative 9.8 meters per second squared. All right. Those are 3 solid pieces of information. So I'm going to say we can start there. Our next step is going to be figuring out, what is it? Yes, what we want to know. So what is the problem asking for? What variables do we care about for parts A, B, and C? So part A says, from what height was it inadvertently dropped? So it's asking for the height. What variable do you think corresponds to height? Well, thinking about our variables, height is going to be related to a change in position. In this case, in the vertical direction. So I'm going to call it, I can call it h initially. So height is equal to question mark, but I'm going to be thinking about delta y, the change in y. All right, part B, how long was it falling? What quantity is it asking for when it says how long? That's asking for the time. How much time did it spend on this fall? And I can write the time as just t if I assume the initial time is 0. That's a common assumption, so I don't need to write it as a delta t here. And then part C, we're sketching graphs. And it's going to be graphs of position versus time, velocity versus time, and acceleration versus time. All right, so we're doing a great job laying this out. Our next step is to brainstorm the tools, right? How are we going to solve this? What equations will help us out? And I just included our 5 super equations here because we know we can use them anytime we have a constant acceleration. Since this is near the surface of Earth in free fall, we do have a constant acceleration. We can use these equations. So what I want you to think about is, for both part A and for part B, which of these equations would allow you to solve most directly for the quantity of interest. So take a look over these equations and write down what you think would work best. You can even try and solve it and see how far you get and then check how it goes. So take some time to go ahead and hit pause now. All right, did you do that? I'm hoping so. Let's take a look. For part A, we're solving for delta y, the change in position, and we don't yet know the time. So that means I want an equation that does not have time. So if I look at my list here, I notice the third equation does not involve time. It has the final velocity, the initial velocity, the acceleration, and the change in position, or displacement. It's not yet arranged to solve for the change in displacement, but I have taken algebra. I know I can rearrange this one. So I think that one's a great one to jot down here. And I'll keep it green to color code it. So v final squared is equal to v initial squared plus 2 times a times, instead of the x minus x naught, I'm going to write it as y minus y naught. Because why not? But also because here we're focused on the vertical direction as opposed to the horizontal direction. So it helps to be a little more explicit. Now, what about for part B? What equation might help us there? Well, notice for part B, we're solving for time. And assuming we did A right, we actually at that point will know all of the other parameters. So we could use any of the other equations. But what I would challenge you is that it's often best to see if you can solve it without needing another part. Many times the problems will be set up that it sort of guides you through the steps needed. But if you don't need to use what you already solved for, then if I made a mistake in part A, I'm okay in part B. So what I'll notice is in part A, what I was solving for was this displacement, delta x or delta y. So equation number 1 does not have that displacement. So I think that's going to be a good approach for B. Writing it as V is equal to the initial velocity plus the acceleration times the time. All right. So now we've gotten quite a bit from these slides, so I'm going to stop sharing for a moment. There we go. So now hopefully you can see the board a little bit more clearly and everything that we've done in writing up here. All right. So first, for part A, we're going to use this top equation, solving for y minus y naught. All right. So I can subtract the v0 to the left side. So I'd have v squared minus v0 squared is equal to 2a. I'm going to make that just delta y to make it a little simpler, a little more compact. And then we'll notice that all we need to do is divide both sides by 2a, and we'll have it solve for delta y. I'm also going to flip what's on which side just to make it a little simpler. So delta y is equal to v squared minus v0 squared divided by 2a. And if you don't like algebraically manipulating things, you can note that up to this point, I have not done anything specific to this problem. I've just rearranged the equation. So you can write down this equation in this form if that helps you out. All right, but now we're to the point we can start plugging in numbers. So let's go ahead and do that. So we have negative 24 meters per second squared minus our initial velocity of 0 meters per second squared divided by 2 divided by a, where my a is negative 9.8 meters per second squared. Now, what you'll notice when you calculate this is we do have a negative in the numerator and denominator, but in the numerator, that negative gets squared. So our final answer here is going to be negative. Is that a problem? I want you to think about that for a moment. I'm going to plug this in. So we have negative 24 squared divided by 2 and divided by 9.8. So that comes out to 29.388. And here, how many sig figs do I have? Well, the 9.8 we take to be perfect, infinite number of sig figs. So what's going to be our limiting factor is the only number given to us, this 24.0. That tells me we have 3 sig figs. So I'm going to report this final answer with 3 sig figs. So I'll first write it out so you can see that I had more. 29.388. And that is in meters, because we have meters squared per second squared divided by meters per second squared. So everything cancels except one of those meters. But we also have a negative sign. So if I write in proper sig figs, we have negative 29.4 meters. Now, it seems a little weird to have a negative sign. Why is it negative? Well, the key is that this is our delta y. Or in other words, this is our displacement. Our displacement, if the wrench is dropped, is indeed going down. It's a descent. So it makes sense our displacement is negative. Or the other way to look at this is it's our final minus our initial. And our initial is larger than our final in terms of height. But we could also write this delta y as, since it's final minus initial, the final, let's see, is my picture still showing here? Yeah, sort of. We could say is at a height of 0 meters. And we could say that this initial height where it was dropped is at h. Now, this is a little bit drawn out, but it's to make a point that I could then plug in final minus initial, so 0 minus h, and this would then be equal to negative 29.4 meters. And so if I solve for h for my height, not for my displacement, I would get a positive 29.4. meters, because we have to keep those units. All right, so there we have part A, cool. Let's go on to part B where we're solving for time. So we already have the equation set up here, but we need to solve for time. So I'll subtract the initial velocity to the left and divide both sides by the acceleration. So that tells me that time is equal to the final velocity minus the initial velocity all over the acceleration. All right, so then let's see, our final velocity is at negative 24 meters per second minus the initial velocity, 0 meters per second. This is where the fact that I wrote things out so explicitly up above makes my life a whole lot easier, because now I've already have it written in terms of the variables of this equation. So I'm just pulling the numbers down. There's much less room for error in translation. So that's why I encourage you to be so deliberate in writing things out. It takes a few extra minutes, but that stitch in time really saves 9. So it's worthwhile. All right, and then we're dividing by the acceleration, which is negative 9.8 meters per second squared. All right, so this time notice we just have a negative divided by a negative, so it comes out to positive, which is good because time should always be positive. So let's take a look. So 24 divided by 9.8 comes out to 2.44898, or we can write that in 3 sig figs as 2.45. All right, and what are the units on this? Well, notice we have meters per second divided by meters per second squared. So what we'll be left with is 1 over inverse seconds, which indeed is just seconds, which is what we would want for time. All right, so we just solved for 2 different quantities using 2 of our super equations. So that's awesome. And as a side note, you can use any of the other equations. There isn't actually a wrong approach in using those 5 equations, assuming you're allowed to use them, because it might just take, you might have to use 2 of them together, but that's totally valid. So if you've solved it another way and got these answers, that's awesome. You can even try it yourself. See if you try a different one and if you can still get the same answers. Right? Our last part is sketching graphs, and I'm running out of room here. So let's pull another whiteboard into the picture. All right, so we want to sketch a graph of position versus time, or displacement. As a function of time, the velocity as a function of time, and finally the acceleration as a function of time. All right, now this can be tricky. What I'd encourage you to do when you have a constant acceleration, start with the acceleration graph. Because in this case, we already know our acceleration is always a single value, right? Acceleration, a is equal to negative g, or negative 9.8. That means that for all of time, the acceleration will just have that one steady value. Negative 9.8 meters per second squared. We won't be able to get away from that. Now, what about the velocity? Well, with the velocity, I encourage you to use the endpoints of what we have above. We know the initial velocity is 0. The final velocity, not the final speed, the final velocity is negative 24 meters per second. So we can put those 2 data points here. The initial is at a velocity of 0, at time is equal to 0. And then at some later time, say there, just note it there, it's all the way down at negative 24. And this is in meters per second. So how does it get from 0 to negative 24? Well, we know the derivative of the velocity is the acceleration. If the acceleration is constant with time, then the velocity is going to have to be a steady change with time, or in other words, a straight line. So we can just do a straight line connecting these two velocity points we have. All right, we can even label this time if we want to, because we found it. That is our 2.45 seconds. Okay, and then finally, what about our position? Well, with our position, we start out at some height. Let's get a different color here. That one was 29.4 meters. And at the very end, we finish at a height of 0. All right, so we know our height as a function of time goes from 29.4 down to 0 in that time interval. Acceleration will still be, well, actually acceleration at that point would be 0 because it is no longer moving. So I technically would cut that off there. Still feels the force of gravity. It's just no longer accelerating. Now, how do we get from the 29.4 down to 0? We could do a straight line connector here, but if we did a straight line connector here, that would be telling us that the derivative of this, the velocity, has a constant value that's not changing with time. And our velocity is constantly changing. So that means we need to make our slope constantly changing, that we start out with a slope that is about 0 and finish with a very large slope, a very steep slope. So a slope that's about 0 at the top is going to be a flat line, and near the bottom it is a much larger value, so it's nearly vertical, and we can fill that in with a curved parabola. It will be a parabolic shape. So there we have our 3 graphs. They are all very interconnected, and it's a pretty involved process to be able to draw them and label each of the relevant points, but it connects to what we just did. The nice part is that anytime we have constant acceleration, they'll follow a similar form. They won't look exactly the same, but the acceleration will always be a flat line. The velocity will be a line that could be going up or down, but it'll be a straight line. And the position will be parabolic. It could be concave up, concave down, any number of things given this setup, given the initial conditions, but it will at least have the parabolic shape. All right, so that pulls us through the example. If you have questions, please ask them in the discussion board or come by my office hours. I would love to talk more about this.